Okay, so welcome to the AI Fun Seminar Series. Today we have Michele Caprio with us, my co-alumni, partly my co-alumni, and he's going to be joining us anywhere, the new faculty very soon. So here's a preview talk. See you.
Thank you very much. So good morning, everyone. Thank you very much for having me here. So this talk is about my main research interest, which is imprecise probabilities and how it intersects with machine learning. Yes, so this is a rough roadmap of the talk. I'll first talk about the historical motivations for imprecise probabilities, what they are, and stuff like this. Then trying to convince you that they're important for ML and AI, and finally talk to you about some research that we've done with co-authors in statistical learning theory. The first two parts are very high level, and the third one is more actual research. So this is a co-author of mine. I still don't have a smiling picture with you guys, so sooner or later I'll change the picture. So if I were to ask any of you if you think that tomorrow it will rain or not, you will likely answer to me either yes or no. Very, very unlikely that you answer something like yes with probability 0.82, right? So if I know nothing else about you, this means that your subjective probability, this is Yusuf, by the way, the probability according to Yusuf that tomorrow will rain is at least a half, and I can't say anything else, right? So these considerations like these were kind of started the study of imprecise probabilities. First in the 60s in philosophy with Henry Heiberg and Isaac Levi. Then in statistics and more in general in STEM with Peter Wolle, who gave a sort of Definitian interpretation to imprecise probabilities, so with bets and gambles, and you can think of gambles as bounded random variables. And then, as of late, with Matthias Troffes and Gerd de Koeman, who extended this to unbounded random variables. Yes, so basically the idea is that the learner is only able to specify bounds for the probability of some events of interest. So this is the very high level and idea of imprecise probabilities. But yeah, fun fact, I'm the academic grandkid of Isaac Levi and Harry Heiberg via Teddy Seinfeld. So what are imprecise probabilities now? A little more precisely, I'm using the definition in what we call the Bible of imprecise probabilities, which is the 1991 book by Wally, where he argues that reasoning begins with the recognition of ignorance and uncertainty. These two concepts are kind of separate, and the latter, uncertainty, refers to how likely facts or events are to happen and are typically measured with probabilities. And this is what in machine learning people call aleatoric uncertainty. And the other part, indeterminacy or ignorance, measure how ignorant we are about facts or events and are typically measured using imprecise probabilities. This is what in ML and AI is called epistemic uncertainty. And in economics, ambiguity. So imprecise probabilities are mathematical models that allow to conduct analysis when both types of uncertainties exist, right? Both indeterminacy and uncertainty. Any questions so far? No, I think, by the way, if you have any questions, please interrupt me. So there are many ways I could have introduced you to these ideas. I thought that going into the statistics first and then moving into machine learning and AI was the most natural way of doing so. So let me start with the imprecise probabilities in statistics. And as you know, there are two main paradigms in statistics, that is frequentist and Bayesian, and we start with the former. Now, in frequentist statistics, before Huber came about in around the 60s, he introduced it, he started robust frequentist statistics. It was believed that small perturbation of the underlying model do not destroy the conclusions drawn from the data. What this means, by the way, because we are in the frequentist paradigm, theta here, the parameter that parameterizes the model, is not a random variable, right? So what this meant basically was that even if I misspecify the likelihood by a little bit, I should be fine. And this kind of reasoning was dangerously wrong. And let me give you a very simple example of why is that the case. So imagine that we collected our data and we plot the histogram. The histogram looks like a bell-shaped curve, centered at 0 with somehow thin tails. We don't know whether they are fat, they are very thin, very fat, but somehow thin tails, right? And we can choose for the likelihood of such model either a standard normal or a standard Cauchy. Now, according to the previous paradigm, right, before Huber, people would say, oh, well, that doesn't change anything, they're very similar to each other, but in reality, things are very different. Hello? And let me show you how. So if we assume standard, the standard normal as our model, we have that the empirical mean is the UMVU estimator of the actual mean, right? It's the best estimator out there. You cannot do better than the UMVU. And you can see this because the variance of the estimator is 1 by n, right? So the more data you have, the more this will concentrate around the true mean. Whereas the empirical mean in the case of the Cauchy distribution, of the standard Cauchy, remains a standard Cauchy. So the shape parameter that somehow governs the variance and the standard deviation is independent of the number of data that we have, of n, and therefore learning from the mean is impossible. This is a very simple example where we see how misspecifying the likelihood gives us very, very different results in our analysis, right? Well, if we're interested in the mean. So what did Huber suggest? Huber suggested suggested something that's called epsilon contamination. Let me. Wow, I didn't see this.
Admit all. You can just click on admit all.
Admit all.
You see the admit all.
There we go. So he suggested to consider what's called an epsilon contamination. And an epsilon contamination looks like the first formula, and it's telling you the following. Say that L is the likelihood that we deem plausible. Consider the set that is whose elements are all the distributions that can be written as 1 minus epsilon times the likelihood that we deem plausible, plus epsilon times all the distributions that have the same support of the likelihood that we deem plausible. Okay, and of course this depends on the choice of epsilon, but that will depend on how uncertain we are about the true data generating process. And this is a very simple visual representation, right? So we have, if we think that our plausible likelihood is the standard normal, we have the standard normal in our epsilon contaminated model, epsilon contaminated set, but also we have a Cauchy contamination of our standard normal. So far so good. Now let me cross the ideological bridge and go into Bayesian territory. So in Bayes, we probably you all know this, but let me go quickly through this. We collect our data, specify their likelihood. In this case, I just for example purposes, I set a normal mean 5. Then we specify a prior. For example, in this case, I wanted to use a conjugate, so a standard normal. And we get the posterior, which in this case is very easy to compute again because I chose the conjugate prior. But then along came the Robertis and Hartigan and Jim Berger in the 80s and asked themselves, wait, are we always able to select the correct parameters for the prior? Right? So why, for example, this is 0.1 and not 0.5, 1.5? And much later, but this also came up. Are we sure that the likelihood that we chose is representative of the true data generating process? This was the result of a dialogue with Huber about robust frequentist statistics. So what they started is the so-called Bayesian sensitivity analysis approach to inference, where they specified a set of priors that once combined in a proper way with the likelihood would give us a set of posteriors, right? And the set of posteriors would then give us a somehow less precise outcome for the analysis, but more robust. And much later, and I've also worked on this, People considered also sets of likelihoods. I'll tell you down the line how these sets have to be proper in this kind of procedure. So in this case, we have a set of prior and a set of likelihoods. They are somehow combined in a precise way, and this would give us a set of posteriors. Now, another fun fact, Jim was on my, although I don't have a smiling picture with him, he was on my PhD committee, so I'm very deep into imprecise probabilities. Now, of course, frequentist and Bayesian are not the only paradigms in statistics, and all the other paradigms that exist out there have been somehow infected by this imprecise way of thinking. From fiducial inference to Dempster-Shafer theory, probability kinematics, and others. That again is not self-celebratory, that is just a paper that we wrote with Teddy, where we show that other approaches like Garden force generalized imaging or James Maxent still can work with imprecise probabilities.
What about outside probabilities?
Which ones are we?
Outside, probability and statistics.
Next slide.
Okay.
In other fields were affected by imprecise probabilities. Here I just put those that I'm aware of because I know the people, right? So economics, game theory, finance, of course, mathematics and engineering, but there are many, many more. Okay.
Because the description that you were making at the beginning, it looked very similar to fuzzy measures.
Yeah, exactly. Fuzzy measures, yes. Here I put it in mathematics.
Okay.
This collecting Scott-Zapapa has to do with fuzzy measures. Yes, absolutely. Yes, fuzzy measures, in their case, instead of considering sets of probabilities, what they do is they consider random sets. So for them, the random variables, the outcome of a random variable is a set. The output of a random variable is a set, instead of being a realization, right? Whereas we derive something very similar, but using sets of probabilities. Okay, but yes, absolutely. So Zadeh in the 80s, Lofty Zadeh. Okay, good. Now, hopefully I gave you like a quick and interesting overview of imprecise probabilities. Let me tell you why they're interesting for ML and AI. Now, I have to apologize here because when you have a Beamer kind of presentation, you have at least one wall text kind of slide. This is that slide, and that's the only one in the presentation, I promise. So robust frequentist, Bayesian sensitivity analysis, and Dempster-Shafer approaches are immediately transferable to ML and AI theory and methodologies. Of course, they are model-based approaches. We specify the likelihood, we specify the prior and stuff. And they are important for three main reasons, or at least in my view, they're important for three main reasons. Maybe there are more. So they account for distribution misspecification and drift, and this is similar to the goal of the out-of-distribution literature. They produce a collection of predicted output that are correct with high probability, and you can see this as being similar to the goal of conformal prediction, and there is a lot of work going on. When I say a lot, I mean mind work going on, how conformal prediction relates to imprecise probabilities. And finally, and maybe the most important thing, is they allow to quantify and disentangle different types of uncertainties in a principled manner, right? So you'll see out there oftentimes many papers or pieces of research claiming that they disentangle these types of uncertainties. It's difficult to gauge epistemic uncertainty, so the uncertainty around the true data generating process, if you're not using sets of probabilities or fuzzy sets and stuff like that. Actually, there is an impossibility theorem that shows that. So, why is this interesting? Because once we have quantified uncertainty in a principled way, we can detect its excess. Not only that, but we can only flag what type of uncertainty caused that excess of uncertainty, right? So if the excess of uncertainty is due to too much epistemic uncertainty, we can fix this. We can retrain the model using data augmentation techniques, semantic preserving transformations, all that stuff. Or if the type of uncertainty that caused the excess is the aleatoric one, so the thing that the analysis that I'm trying to solve is actually too difficult for a machine, we can query for human help. This is typically the case for medical applications, right? Where we have a mole or a skin lesion, it's very difficult to see. We then ask a doctor. Any questions so far? Good. Now, of course, we have to pay tribute to the pioneers in this field, which all started, by the way, in the early 2000s. The first problems that were studied were classification problems with evidential neural networks and naive Friedel classifiers, which are in a certain sense similar to conformal prediction, but they require you to specify a model, right? So they're not model free. And what they say is basically after training and given a new input, the new input goes through this procedure, which is designed to be robust to distribution misspecification and distribution drift. And the output is a collection of labels that are correct with high probability for the input that we use. The only difference the main difference with respect to conformal prediction, on top of this not being model free, is that you cannot control the probability that governs the output, the label output, right? So, which means that the set of probabilities itself will tell you which are the higher probability ones. You're not in 1 minus alpha, you don't choose that, okay? And then we have causal inference with Friedel networks, vision with evidential object tracking, and dynamical systems. So these were the first applications of imprecise probabilities to machine learning and AI. And of course, nowadays, the amount of work exploded, both in methodology and theory. Here, I just put some references for the interested people. I've worked on a lot of these fields. I would very much like to work more on reinforcement learning and medical applications. So if you're interested and you have some experience in these, reach out. I would really like to collaborate. For the rest, we have active learning, continual learning, Bayesian learning, evidential conformal prediction, causal inference, and so on. And of course, more on the theoretical sides, we have properties of uncertainty measures, IPs in general, the IP theory, probabilistic programming, Markov chains, and relationship with conformal prediction. These more on the theory side. Now you'll see a lot of my name here. Again, this is not a self-qualification. It's just that I'm comfortable talking about these things with you if you want. And I'm also happy to share the slides then if you want to. But if you're more interested in imprecise probability theory, you should look into the website for the Society for Imprecise Probabilities, SIPTA.org, or the Journal for Imprecise Probabilities, that is the International Journal of Approximate Reasoning. And talking to you about some imprecise probability theory, and in particular, about statistical learning theory. Before I start, any questions so far about what I've said? No? Good. So, I'm sure that all of you are familiar with statistical learning theory, but just bear with me for a couple of slides where I especially explain the notation and whatnot. So statistical learning theory is the foundation of machine learning, of course, and it provides theoretical bounds for the risk of models learned from a single training set. This is the classical one, which is assumed to issue from a single unknown probability distribution. What is the problem? The problem is predicting an output given an input and using a mapping, which is the model, which belongs to a space of hypothesis calligraphic H. We have a loss function, of course, and the latter measures the error committed by a model in predicting the output. I will use throughout this last part of the talk the 0-1 loss, and we use it throughout the paper as well. The reason why we did this is that we wanted to directly generalize the classical results. So if you open a book in statistical learning theory, the first loss that they use is this 0-1, and of course in the future we plan to generalize this to other types of losses. Input-output pairs are usually assumed to be IID from an unknown probability distribution that we call P star. Right. So what a quantity of interest is the expected risk or expected loss, right? Which measures the expected value of our hypothesis, of our model, with respect to it measures the expected value of the loss with respect to the true distribution P star. And of course, the best models are those that minimize this loss, right? The one that live in the arc mean of this expected loss. But in real life, P star is unknown, and so we turn our attention to the empirical risk, okay? And from the empirical risk, we derive the empirical risk minimizers. So all the models that minimize the empirical risk, okay? So far, so good. Okay. And the next step, of course, is we want to bound the excess. We want to, do I have a model now? So we want to bound the difference between the empirical risk minimizer and the lowest expected risk, right? We want to bound the difference between this guy and this guy right here. And we want to do so under increasingly more relaxed assumptions about the nature of the models that we use. Today, I will only consider the case where in these slides, all the assumptions that I'm going to tell to you now. The paper, we also have the more general version. Actually, also in the appendices to the slides. So typically, you start saying that the hypothesis space is finite, and that there exists a model with zero expected risk, right? The one that actually minimizes the loss. That's called realizability. So this is what classical statistical learning theory does. Now, we asked ourselves with my co-authors. This is a paper co-authored by people at Oxford Brookes. We asked ourselves, what should we do when distribution shifts are allowed? This may cause issues of domain adaptation or domain generalization, and people have studied these kind of problems, but under kind of strong assumptions. And okay, we have a deep review of the attempts that other people did. And instead, we wanted to use something more natural, more in line with what I've told you before about imprecise probabilities, that are priddle sets. Can you remember when I told you I'll tell you down the line what those sets in the Bayesian case will be? These are priddle sets, and they are the following. A priddle set is a set of probabilities that is convex and closed in some topology. Okay. And a finitely generated priddle set is a priddle set whose extrema are finitely many. So the number of elements of the priddle set that cannot be written as a convex combination of one another is called, if that cardinality is finite, then the priddle set is called finitely generated priddle set. Now you have two very simple examples here. On the left, we have on the left you have a priddle set in a discrete space. So imagine that the state space is three-dimensional, so y1, y2, y3. Now, in this case, a probability distribution can be written as a probability vector, right? Because, say, 0, 6, 0, 6, 0, 3, 0, 1 is a probability distribution on these three labels, and you can put it in a vector. So once you put it in a vector and you see it as a probability vector, you see that the probability vectors all live inside of the unit simplex, so the purple triangle. And the orange pentagon is a finitely generated priddle set having 5 extreme elements. Okay, all the vertices of the pentagon. Instead, if the state space is uncountable, this is a very, very simple example. You have in this example, you have two normals, which are the 2 extreme elements, again, a finitely generated priddle set. And in black, you have one element of the priddle set that can be written as a convex combination of the 2 extreme elements of P1 and P2. So Q is a convex combination of P1 and P2. Okay? And all the possible combinations live in the priddle set.
So the convex hull of any finite number of probability distributions is a Criddle set which is finitely generated.
Exactly. It's called finitely generated. Yes. Yes. Because of course it's yeah.
So from Bayesian non-parametrics, yes, we just have a prior over the set.
Yes. So the main okay, in statistics, these problems were studied in the 90s, early 2000s, and then people moved away because Bayesian non-parametrics became more popular. And yes, you're absolutely right. What I don't like very much about Bayesian non-parametrics is that from a statistician point of view, you lose a little bit of interpretability, right? It's very hard to interpret a Gaussian, like the parameters of a Gaussian process. Whereas this allows you to retain the interpretation of usual parametric distributions while also pursuing the same goal as Bayesian non-parametrics. And this is the reason why I enjoy this literature a lot. I suppose also that this kind of interpretability could play a role into explainable AI. And I know there are some people at LMU in Munich that are working on this. But I don't have a deeper answer. Other than you're absolutely right. Yes, you can look at say a Gaussian process as a second order distribution. So from an imprecise probabilistic point of view, Bayesian non-parametrics is part of imprecise probabilities at large, right? Because it's another way of expressing epistemic uncertainty in our words.
In this case, I'm just referring more to sort of the Dirichlet process, for example.
Exactly. That's perfect. Yes, the Dirichlet process is the second order version of having a set of categorical distribution or multinomial distributions. So yeah, you can use either. Actually, there is a lot of literature, and some of it I also cited in the slide that I had before, that it shows that second order distributions, because of how they are elicited, somehow tend to underestimate epistemic uncertainty. So people prefer using Criddle sets for that extent. But from an applied point of view, they do the same thing. So it's actually whatever you prefer, whichever is faster if you're a practitioner. Good. Now, okay, so this is what we do. So instead of having one single training set, we assume to have a sample of training set, and we use this sample of training sets to generate a Criddle set of distributions, and then we use this Criddle set to generalize the bounds in the classical statistical theory, and actually this allows us to have tighter bounds. Okay.
So is this also connected to boosting then?
I don't know. Maybe. I haven't thought of it.
Okay.
But I think it's a little different. You'll tell me in a second. So what do we mean by sample of training set? So instead of having a single training set, imagine that you're in a continual learning scenario where you have a continuous flow of data for different tasks. Okay, so D1 is the data that pertains to task 1 up to the end that pertains to task n. Right? All of them have. This is a very notation heavy, and I will make it less heavy in the next few slides, but it's telling you the ith dataset is composed of xi1, yi1. So the first element of the ith dataset xi, xy, and so on. The nth element of the ith dataset xi and iyi. I will make it less unappealing in a few slides. We assume that they are distributed IID from an unknown distribution, P star I. And of course, the distribution need not be the same for all datasets. So D1 can come from P1, D2 from P2, D3 from P3, and so on. Now, there are many ways of performing this task, right? Going from the training sets to the cradle set. Now, here I give us one of the approaches that we have in the paper that is an objectivist approach that has to do with the robust frequentist one that I explained at the beginning. So for every training set, we specify a likelihood, and we perturb the likelihood using the epsilon contamination. And once we have I many such likelihood, such epsilon contaminations, I consider their convex hull, and that convex hull is going to be our cradle set. Okay, let me give you a simple example. So imagine that the state space is omega 1, omega 2, omega 3, where omega is the pair xj, yj. Omega j is the pair xj, yj. And we observed 4 training samples, D1 through D4, and we specify 4 likelihoods that look like this, right? I just filled with some numbers. And after I have these likelihoods, I choose 4 different epsilons for all the likelihoods to perturb them. So to obtain 4 different epsilon contaminated sets. Once I have the 4 epsilon contaminated sets, I consider their convex hull. And now that I have their convex hull, it's easy to see the lower and upper probability. The lower and upper probability, I haven't talked to you about this before, but it's basically the lower envelope and the upper envelope of the cradle set, right? So the lower probability is the minimum probability that a set can have within that cradle set. And the upper probability is the same, is the conjugate concept. Am I making myself clear on this? Basically, what I'm saying is the general definition of lower probability is the infimum of the p's of the distribution in the cradle set of PA.
I'm a bit confused. How are you getting the LI information? Where is this LI going to come from? All you have is the training data. Just by looking at training data, how do you know LI?
You specify it, right?
So specify means what? Like, what is specify?
You can use, for example, the empirical distribution, which is a non-parametric estimation of the likelihood of the true likelihood.
Yeah, I'm a bit confused. How is this L1 specified just by looking at one sample of the training data?
No, it's not one sample. Sorry, it's you have many samples within each of these. Like D1 has n many elements in it. So it's like this. But so we see.
Okay, D1, so your DI is a sample, training data sampled from the omega space.
Exactly.
And you're looking at the empirical distribution over the sample space from DI.
Exactly. For example.
And that is LI.
Yes. For example, yes.
LI is an estimation of the distribution DI.
Is an estimation of PI star. Yes,
PI star.
Exactly. And because we don't know it for sure, we perturb it with the epsilons. Okay.
There was something called PI also, right? Am I getting confused? Wasn't there a PI? Yes, good. Okay, so there's you only had PI star.
Yes.
PI star is a true distribution of the ith data set.
Yes.
And LI is your empirical estimator of PI star.
Exactly. And you can perturb it as we did here.
What is Q?
Q is any distribution that has the same support of the S. So basically, this is saying consider all the possible distributions on the space omega. As long as it has the same support, we are considering an epsilon approximation, an epsilon contamination with all distributions, and all probabilities that can be written as a perturbation, as this kind of perturbation goes into this set value. Okay, so they are kind of big. And then on top of them being big separately, we consider their convex hull. So we sort of consider their union in a certain sense. And I just want to say that the lower and upper probabilities are computed in this way. Okay, so the maximum and minimum value of the probabilities within this larger set. And basically, these are the numbers, and this is the visual representation. So for for the element omega-1, we know, given the data that we have collected, that the true probability will be between 0.09 and 0.58. For omega-2, between 0.08 and 0.82, and likewise for the other elements. So this basically gives you an interval. Okay, so the true one will be between which is the lower bound of the interval, and the upper bound of the interval, and for all the other elements as well. And that is a visual representation. So you see how, despite we observed 4 data sets, we still have a pretty big Friedel set compared to the simplex, which is, again, I chose only a 3-dimensional set so that I could plot the picture. Yes.
So the I values of epsilon and the distribution Q are quantities that you choose that don't depend on the data, right?
Yes, exactly.
Okay, can I interpret the epsilons as sort of like the amount you believe your data
100%.
and Q is just sort of some like agnostic?
100%. Yes, that is the correct interpretation, especially if you're a subjectivist. If you're a subjectivist, that's exactly what it is. Yes, yes. And there is some literature where they go even further. Instead of perturbing just using just one distribution here, although you do it for many of these Qs, they have different Friedel sets here. Okay. So it's even more, it buys you even more uncertainty. Okay, so far so good. Awesome.
So you didn't say what is Q here.
No, it's all the distributions on the omega-1, omega-2, omega-3 space. Good. Okay, now I told you one way of coming up with a Friedel set. In the paper there are many more, a few more. And now the next step is to tell you how do we obtain the generalization bounds. Okay, so this is, let's say, the first main theorem that tells you the following. Okay, so this is the ugly notation of before, so let me ease it. So now we are in the n+1 data set, and we observe n sub n+1 many new data points. And let me denote these by x1, y1 through xn, yn, just for notational purposes, so that I don't have to use this notation here, which is there. And assume that they are sampled IID from a distribution P star n+1, which again I refer to as just P for notational purposes. And we assume that it belongs to the Friedel set that we derived before. Okay, so this is kind of a crucial assumption. And it's some may say a strong one. And in the future, of course, our idea is to derive a sort of a pack-based guarantee that actually this is true somehow probabilistically. But for now, this is very reasonable, especially if the sequence of data sets that we collected pertain to tasks that are similar to each other, close to each other. Okay, so it's in that case, it's kind of natural to assume that the data for the n+1 task will be from a distribution that is somehow close from the Friedel set point of view to the ones that we saw before. Recall that the empirical risk minimizer is h hat that belongs to the argmin of the empirical loss. And because we are in the best case scenario possible, we assume that there exists a realizable hypothesis. That is, there is at least one H star for which its loss according to the true distribution P is 0. We assume that the model space is finite. And we use the 0,1 loss. Okay, this is, I told you why we do this. What we find is that if we fix any delta, we derive a value epsilon star of delta for which the probability of the loss according to the true distribution P associated with the empirical risk minimizer H star. This, of course, a more complete version would be -0, right? and it would be the distance between this and the loss of the true data of the true realizable hypothesis, but this is 0. So imagine that here is LP of h hat minus 0. Okay, so the probability that this error is small is greater than 1 minus delta, and this epsilon star, of course, depends from delta. And epsilon star is a well-defined quantity, which only depends on the extreme elements of the Cradle sets. So only on the elements that cannot be written as a convex combination of one another, which means, sorry, that if the Cradle set is finitely generated, this is very easy to compute. Yes.
When you say P star n plus 1 congruent P, you mean every...
No, sorry, not congruence. Yeah, this means equal. Like I just say...
Which means every training data is from the same distribution.
No. I'm just saying, no, sorry. I'm just saying that instead of writing P star n plus 1 here and here, I just write P for notational purposes. Only these come from P star n plus 1. All the other ones come from P star 1, P star 2, P star n that we use to derive the Cradle set calligraphic P. So this is a new...
The risk, the LPH hat is the risk in the distribution of the last data.
Yes, exactly.
Why is the distribution of the last data important? Why are you picking out on that distribution, not all the distributions that happened previously? Your setup is that every training data is a sample from a different distribution.
Exactly.
But when you're computing the risk of the estimated H hat, that's the risk in only the distribution of the last data.
Yes, but I'm only using the last data too. Because those ones I've seen already, this is new. Those I've seen, and I've used to, the ones in the previous steps, I've used to derive the Cradle set, right? So it's what we've done here. Right now I have this Cradle set, okay, and now I see
your setup is like you have a training data where every training data is a sample from a different distribution.
That's exactly right.
You construct an estimator based on this.
Yes.
But you want to compute the risk of the estimator in the distribution of the next one, which has never actually occurred.
That's exactly right. Yes. And the only, again.
But all that you're guaranteed is that the distribution of the n plus 1th data is part of the Cradle set.
Exactly. That's what I require. Yes.
But it's completely unknown.
Yes, exactly. That's what I require. Yes. And that's why it's kind of that I was saying before, it's kind of a strong assumption, but yeah, in the future we will try to have it in a probabilistic form, sort of a pack base. Like we want to transform this assumption into a lemma, saying P, the probability that the true distribution belongs to the Cradle set is at least 1 minus alpha, something like that, under some conditions. Does that make sense? Okay. Yes.
So the realizability assumption applies only to the n plus 1th environment, not
yes.
If you're assuming that the likelihood is changing in each environment, does it actually imply that the hypothesis class isn't realizable in the previous ones? Or like, does it imply kind of anything about the realizability of the hypothesis class?
Yeah, no. We don't care about the previous ones. The only thing is that that's actually a good question. So the second assumption must be true for the previous ones as well. So the fact that the hypothesis space is finite must be true for the previous ones, because otherwise it can do it. But this one, no. Like the realizability, we only need for the n plus 1. I don't know if you can see the n plus 1.
And if I somehow assume that the distributions of the data sets P1, P2, P3 are not changing too much, like there's a very little drift.
Yeah.
Which part of this will improve? Something should get very better, right? Something should.
Yes, that's for sure.
Which part will get much better if the drift is.
I think this one. Actually, yeah. You know what? It will improve. The bound will improve when the number of sets is small. The number of observations is small. I'll show you in a second why I mean this.
Something should improve if I assume that the distributions are not changing too much. Where is that? There should be some parameter which is proportional to how much the drift has been.
So I'll show you this. So we have in this corollary the fact that you can compute the loss with respect to a different distribution, to a wrong distribution, and still have a bound. And this bound depends on the diameter of the set, of the Cradle set. So if somehow you're able to say that the distributions change very little, maybe this diameter will be very small. And so even if we compute the empirical loss with respect to the wrong distribution, then we will have a similar bound.
I think we need some kind of a theorem is needed which says that if the drift, if the distributions from the ith to ith plus 1th data are changing by only epsilon in TV measure or Wasserstein measure, then the Cradle set cannot become too large.
Yes,
Is
I
there
like
such a
this
theorem?
idea. I like this idea, yes.
Is there such a theorem?
Not yet, but I like this idea.
Yeah, that
Yes,
seems like a very necessary theorem we should prove.
yes. This
Small drift should make the Cradle set small.
exactly. This is all the like follow-up work. In one is this, and the other one is okay. Now that I have this condition, then maybe making this assumption not an assumption anymore becomes kind of
Yeah, I mean, I also it's a bit surprising the eta doesn't occur here, or are you hiding the eta in epsilon star? That there is this extra factor eta.
Oh no, okay, this is in the corollary. No, in this case it doesn't play a role.
Why? Why does the eta disappear in this case and only appears it's the same, right? The setup.
Setup is the same, but basically, if instead of computing the expected loss of the empirical risk minimizer with respect to not the true distribution, but another distribution in the set, whichever you want to pick, which is not the correct one.
Which is a bit confused about why is Q different from Pn plus 1? Q and Pn plus 1 are the same things, right?
Yeah, I mean,
it's equally unknown.
Yes, exactly. But that's why I put here this go to corollary for 3. So this corollary is kind of useless. I just wanted to put it there because it's nice. So basically, you have your Cradle set, and you have the true unknown correct distribution, right? And the Cradle set has its own extreme. And here I'm saying, if instead of computing the loss with respect to the true distribution, but some other distribution in the set, then the diameter of the set plays a role in how much my bound gets worse with respect to the
Why
correct
does the
one.
diameter not play a role when in this theorem? But this theorem and the corollary are identical, right? I mean,
Yeah, no, because here in the proof I'm only using the extreme elements. In the proof of the theorem, I'm only using the extreme elements, which
there's something getting very confused. Why is? Yeah, you're saying epsilon star delta is the same as in theorem 4.
yes. But it becomes like the bound becomes worse because now I'm computing the loss with respect to another distribution, which is not the true one.
Why is another distribution Q different from Pn plus 1 star? Pn plus 1 star is a candidate Q, right? Like conceptually Q and Pn plus 1 star are different, right?
Yes.
Are the same.
Why are they the same?
That's what I'm not understanding. Why are they different? Like Q is any L prime distribution in the Cradle set. That's the only condition on Q.
Yes, I see. Okay, yes. Okay, yes. If you use any Q, then this is the result that you have. If instead you use the correct one and you say that you know what it is, then you can obtain this bound. And this bound is
okay. So I guess the difference is you're not assuming realizability in Q. So the difference is that Q, you are not realizable in Q, but earlier you were realizable in Pn plus 1. Is that the difference?
I think so, yes.
Okay, so that is where the issue is then. Okay, Q is more general than Pn plus 1 because you are not assuming a realizable in Q.
That might be it, yes.
Okay, so then that is why this diameter of the Cradle set is now an extra error.
It plays a role, yes.
Yeah.
Okay, this is what I told you.
Sorry, just another couple clarification questions that I think build on what Anna may have been asking. So in this corollary is H hat the empirical risk minimizer of P or of Q?
P.
Okay.
P.
And then I guess because so you have the realizability assumption in the theorem, but because the distributions are changing, is it? Wait, sorry. sorry, so in the theorem, was H hat the empirical risk minimizer on 1 to n, not on n+1, right?
What?
So H hat is the empirical risk minimizer on the data from environments 1 to n, not the empirical risk minimizer in environment n+1.
No, it's the empirical risk minimizer in n+1.
Oh, okay,
In S-
okay, cool, yeah.
And I have so this is the other corollary that tells you basically that the bound that we find in theorem 3.1 is a sharper bound than the classical statistical theory one. And the reason is that basically this is the classical one, the classical statistical theory. And instead of having the logarithm of the cardinality of the whole hypothesis space, we only have the logarithm of the union of the bad hypothesis according to the extreme elements. This is kind of complicated, but basically we have that our bound is smaller, and the big O that we provide is faster as well. And let me give you a simple example. So imagine that
Are you sure you don't have a typo there?
where
This is square root n, right? Not n. This is log mod h by root n, right? Not n.
I think it's I'll show you that, like, if you check in this Liang 2016 theorem 4, they use a
Root n, I thought, okay.
anyways. So let me give you a simple example. So imagine that the available training set are D1, D2, D3. And for simplicity, we assume that omega is x times y, and to make things easier, x is a singleton. So x times the whole real line gives us, it's isomorphic to the whole real line. Now, suppose that we specified the likelihood PDFs L1, L2, L3. L1 is a normal on -5, -5, 1. L2 is a normal 0, 1, and L3 is a normal 5, 1. Call calligraphic L1, L2, L3 their probability measures. And we consider as a critical set the convex hull of these three distributions, and so that the extreme elements are the three distributions themselves. Let now dn+1 be a collection from n samples, and because the experiment is synthetic, we assume to know the true distribution, which is, we assume it is L2, so it of course belongs to the critical set. And we assume that the assumption that we have in the theorem are satisfied, so the hypothesis space is finite, and it's a set of some simple binary classifiers containing at least one realizable hypothesis, and we use the 0-1 loss. And what we have is the following. We have that when the number of samples are small, our bound is much tighter than the classical one. And instead, when the number of samples become large, then the two become basically very, very similar to each other. And why is that? The reason is that with a few samples available, that is when the cardinality of the fourth training set is low, then critical learning theory leverages the evidence in the critical set. So instead of having to consider all the possible distributions, we only consider those who come from what we know from time 1 to 3. So a much tighter bound is achieved. And instead, when the sample size is large, the uniform bound of statistical learning theory is itself very small, because the average loss well approximates the actual loss, the true loss. And in turn, since the universal bound is already small, then the critical learning theory bound that we find is only slightly tight. Okay. And yes, then we consider the case where we allow distribution drift in the n+1 training set. And in this case, what we have is that the bound becomes a little less tight, of course. Okay, ideally, we would want to have just something like smaller or equal than 2 times what we had before, right? Because I'm saying like now from 1 through k, the elements come from one distribution, and from k plus 1 through n they come from another one. But that is not possible, or at least I wasn't able to show it. So that is the best that I have. So epsilon star delta is the same as theorem 1, as of the theorem before, and it has to be, somehow improved, changed to make the corollary work. Well, of course, like h hat 1 and h hat 2 are the empirical minimizers of the 2 distributions. Yeah, so this is what we have so far, and then within the paper we relax first the realizability assumption, and we keep H finite, so the model space finite, and eventually we relax everything. And in this case, Rademacher complexity plays a role, but I don't want to overload you with. I've spoken for an hour already. So just briefly what I'm trying to do in the future, as I was telling to Anil bit and you all before, I plan to extend our results to different losses, right? Again, we only used 0, 1 because we just directly wanted to extend the traditional distributions and the traditional statistical learning theory results, and derive pack-like guarantees on the correct distribution being an element of the critical set. I think here Anil bit had a good suggestion, maybe somehow being able to work on the diameter of the critical set in some metric may bias these guarantees. And finally, validate our findings on real data sets. This is kind of difficult because you don't have the true distribution, so you can't have those kind of results that I've talked to you before. And to conclude, just an open problem in imprecise probabilistic machine learning. It's an afterword by Marco Zafalon, who used to be the head of the president of the Society for Imprecise Probabilities. So we would want probabilistic machine learning to get closer to scientific methods. And what he said was that science needs falsifiability. So purely probabilistic models aren't really falsifiable because they're at most improbable, right? That's the reason why we have so many different theory of probabilities: subjective, objective, radical probability, and so on. So he says, it seems to me that the scientific method is based on causality, and imprecise probabilistic machine learning is very well equipped to deal with causality. And maybe this ability of merging causality and taking into account the imprecision that we are facing is the way to go to get PML and IPML close to scientific methods. So thank you for your attention, and please consider joining the Imprecise Probabilities Society and seminars. Thank you very much.